limits. The limits you have probably seen in your Calc 1 class. However, today we're going to get to a rule called L'Hopital's rule. And you may have seen that already, but when we get to sequences of series, even with some of these improper integrals on your homework lessons, you're going to want to use L'Hopital's rule. All right. So let's get started. Example 1 says evaluate the following limit to show all of your work. So what I want you guys to do is pause the video for just a few seconds and go ahead and do 1A, 1B, and 1C. Again, you should have seen this before. If not, we're going to go through it quickly, but we will go through it. All right, welcome back. So, example 1, evaluate the following limit, show all your work. Or it can be a T-table, it can be algebra, whichever you guys decide. I normally stick with T-tables, but on some of this, I will use algebra. So A says the limit as x approaches 2 of x minus 9 over x minus 4. And we are going to simply plug in 2. And so we get the 2 minus 9 over 2 minus 4. And I'm just going to go ahead and plug this into my handy dandy calculator. So we have, I'm going to use parentheses, 2 minus 9 divided by 2 minus 4. And we get 3.5. Oh. Okay. And what this means graphically is if we go to the x value of 2, go up to the graph, the y value so we go to the x value of 2, we go up to the graph. This x value, this y value is 3.5, which we can see there. So that's what the limit is confirming. If we come in from the left, we come in from the right, we meet right there, our limit is 3.5. Okay, so that's part A. That's your very basic limit. Now, when we look at B, we have the limit as x goes to 4 of x minus 9 over minus 4, so the same thing. However, if we just plug 4 in, we get 4 minus 9 over 4 minus 4. However, this gives me negative 5 over 0. Problem, we can't divide by 0. Different approach. I just really like tables, and then I'll show you graphically what's going on. So I'm just going to erase this so I have enough room. So if I make a T-table, I'm going to look at what is x doing when I'm getting close to x from the left hand, or close to 4 from the left hand side. So I'm going to look at numbers like 3.9. That's pretty close to 4. 3.99, a little bit closer to 4. 3.9999, a little bit closer to 4. So numbers getting closer and closer to 4, but never actually reaching 4. And I'm going to use my calculator for this. So I'm just plugging these numbers in for x. So I have 3.9 minus 9 divided by 3.9 minus 4. And I get 51. Okay, so I want to get a little bit closer to 4. So I'm going to type this in. So second, enter. brings my problem back up. And if I want to insert a number here, I'm just going to press the blue key, which is second, and then the delete key, which gives me insert. 9. 501. And I'm going to get a little bit closer. I'm going to add a few more 9s in there. Just a second. Enter. Second. Insert. 9. Make sure to do this with both your 3.9, 9s. Insert. And we get 50,001. So as X approaches 4 from the left-hand side, this right-hand side is going off to positive infinity. So writing that with limits to limit as X approaches 4 from the left-hand side of X minus 9 over X minus 4 is infinity. Okay, so now we need to come in from the right hand. What's going on there? And I'm going to come under graph so we can do that. So if I start at 4.1, I might do 4.01, 4.001, 4.0001. Okay, and I'm going to plug these in my equation. So we have 4.1 minus 9 divided by 4.1 minus 4. I get negative 49. And then if I plug in 4.01, negative 409. And so I'm just going to keep doing this. And I'm going to add in more zeros. Negative 4,999. We're going to add in one more 0 into our 4.0 sequence. So we have 4.0001. And we get negative 49,999. So what we're seeing is as X is going to 4, Y is going to negative infinity. So writing the limit as X approaches 4 on the right-hand side of X minus 9, X minus 4 is negative infinity. And so because the limit coming from the left and the limit coming from the right do not equal the same number, this limit just simply does not exist. And so graphically we can see that when we approach this from the left-hand side, this shot up. When we approach this from the right-hand side, this went down to negative infinity. It's kind of like they're missing each other. And so it just does not exist. Okay. So sample 1 says evaluate the following limits to all of your work. And now we're looking as X approaches infinity of X minus 9 over X minus 4. Table. infinity, we're getting bigger and bigger in numbers. I start at 100, 1,000, and then I go 100. See what is going on with the y's as my x's are approaching infinity. Okay, so let's plug this in. We have 100 minus 9 divided by 100 minus 4. Then we get 0.94 to 1,000. Go in here, and instead of 100, then 1,000. Then we get 0.995. And maybe do 100 times. Let's add 2 more zeros. You want to add more zeros, go for it. So when I do that, there we go. So we get 0.99. So notice, as my x's are getting larger and larger and larger, my y's they're not getting huge, but they are getting closer and closer to a particular number. We have 9.4, 0.995, 0.99999. So these are getting closer and closer to 1. So this limit as x goes to infinity of x minus 9 over x minus 4 is 1. This graph right here is not a very good graph. What would happen is it would flatline there at 1. So as x goes to infinity, y is going to go to 1. Again, you can do algebra if you really want to do algebra. These tables work just fine, especially since we're just trying to get to a rule called L'Hopital's rule. Now, all of these limits, we were able to find an answer using t-tables or even using algebra. This one just does not exist. This one we can do a little algebra on if you wanted to. I'm just not. If you want to see that video, I can share that video with you. But, you know, as the x's go to infinity, y's go to 1. So let's go to example 2. Example 2 says evaluate the following limits, show all of your work. So we're taking the limit as x goes to 1 of x squared plus 4x minus 5 over x squared minus 1. And so we want to know when x is 1, what is our y value? And we can see from here that y is going to be 3, just graphically. So how would we do this? The first way we can do this is a t-table. The first way we would normally do this is to plug 1 in. I'm jumping ahead and assuming that we already know that it's not going to work. Okay, so if I was to plug 1 in, we would get 1 squared plus 4 times 1 minus 5 over 1 squared minus 1. And this gives us 0 divided by 0. This is not really an answer. Really do this. So going to our next page, so we have more room. It says evaluate the limit. So it's the same thing. We're talking about something called L'Hopital's rule, and I'll come back up to that in just a second. So we could do this using algebra. We have the limit as x goes to 1. We could say this is x plus 5, x minus 1, over x plus 1, x minus 1. The 1's cancel. And so then we can plug our 1 into x plus 1. So we get 1 plus 5 over 1 plus 1, which gives me 6 over 2, which is 3. Okay, that requires knowing this rule, or you can make a t-table. Again, we can see from the graph when our y value is 1, our x value is 3. Okay, so coming up to L'Hopital's rule, it says recall, but you guys might not have learned it before. Some of you have. It says if our limit is indeterminate of the form, guys, this is a really big deal. It has to either be 0 over 0 or infinity over infinity. Now, I will tell you for my students, this makes a great test question. You know those test questions where Tim's arguing with someone and he gets this answer and he does L'Hopital's rule? Well, it's probably going to be because it didn't work out right because he did not check to make sure it was in the right form. So just a heads up, my students, great test question. Okay, so if our limit is indeterminate of the form 0 over 0 or infinity over infinity, which we had 0 over 0 on this problem, then the limit as x approaches a of f of x divided by g of x is the same thing as the limit as x approaches a of f prime of x over g prime of x. So let's do that down here. So note, we had the indeterminate form of 0 over 0. And so we can say the limit as x approaches 1 of x squared plus 4x minus 5 over x squared minus 1 is the same thing if we use L'Hopital's, which is spelled L'Hospitals. And when I take this derivative, I get 2x plus 4. So take the derivative of the top. So the top is x squared plus 4x minus 5. I'm going to take that derivative, and I'm going to divide by the derivative of the bottom, which is 2x. Okay, and I forgot to write my limit sign. So this is really the limit as x approaches 1. I think I said it. I just forgot to write it. And so now I'm going to plug in 1. So we get 2 times 1 plus 4 over 2 times 1. Hand it in to calculator. And so I have 2 times 1. 2 times 1 plus 4 divided by 2 times 1, which is 3. Now, if we had used L'Hopital's rule and we had still gotten infinity over infinity or 0 over 0, then we can use L'Hopital's rule again. But you have to make sure you're getting that 0 over 0 or infinity over infinity. All right. So our last page of our limits, example 3 said evaluate the limit as x goes to infinity of x cubed plus x over x squared minus 6. Now, if I just plug infinity in, we would get infinity plus infinity. So we get infinity on the top. Infinity squared minus 16 is infinity still. So we get infinity over infinity. So we can use L'Hopital's. So use L'Hopital's, and we get the limit as x approaches infinity, take the derivative of the top, which is 3x plus 1, 3x squared plus 1 over 2x. Now, if I plug infinity into this, I get infinity on the top divided by infinity on the bottom. This is still infinity over infinity. So I'm going to use L'Hopital's again. And so we get the limit as x goes to infinity of 6x over 2. Now notice, I plug infinity here, it just is infinity over 2. That is not indeterminate, so we can't use L'Hopital's again. But what we do get is 3 times infinity, which is just infinity. And we can see that here. So this one shoots off, and it just keeps going. So as x goes to infinity, y, notice here, it shoots up, y also goes to infinity. But we were still able to use L'Hopital's to show that. Okay, sample 4, love this problem, great test problem. Sample 4 says Eli is calculating the limit as x goes to infinity of 3x over 5x plus 4. He claims the limit as x goes to infinity of 3x over 5x plus 4 is 1 because you get infinity over infinity, which is equal to 1. How I would respond? Yes, but I would say, Eli, I would tell you that infinity over infinity is an indeterminate form and the infinities do not cancel out because we don't know if one infinity is larger than the other or smaller than the other. So we don't know the answer of this. So infinities don't cancel out. We can't really subtract them. We can't really add them. If we have an infinity plus infinity, it's just another infinity. We can't say when they subtract that it goes to 0 if we don't know how they're approaching in the same way. So to solve this, since the limit as x goes to infinity of 3x over 5x plus 4 is equal to infinity over infinity, we can use L'Hopital's hospitals on this problem. Okay, so I tell Eli, hey, we can use L'Hopital's on this. And the big key word here that I would look for on a test is this is an indeterminate form. And because it's an indeterminate form of infinity over infinity, we can use L'Hopital's. All right. So let's go ahead and look at some improper integrals. So I want to note here that we can't just, first off, it says example 6, estimate the integral from 2 to infinity of 4 over x dx. Okay, we can't just straight out use the fundamental theorem of calculus, because the fundamental theorem of calculus says that we are going from one number to another number. And then when we can calculate it, it also states that it's continuous on its domain. So infinity is just approaching infinity. It's not a number. So we have to rewrite it. So the limit, and you can pick a letter, any letter. We're going to rewrite this as the limit. I'm going to say t goes to infinity, the integral of 2t 4 over x dx. So we're going to use t as a placeholder like a number, but it's going to be a placeholder for us. Okay. So now we can integrate this. And this becomes the limit as t approaches infinity of 4 ln of x evaluated from 2t. Okay, so now we can use the fundamental theorem of calculus. And so we get the limit as t approaches infinity of 4 ln of t minus 4 ln of 2. Okay. So now we can take this limit. If you remember the graph, 4 ln so 4 y. So when we take this limit to infinity of 4 ln of t, what we get is infinity minus 4 ln of 2, which is just infinity. Okay, so we're saying there's infinite area under the curve from 2 to infinity, because remember, when we're taking a definite integral, we're finding the area under the curve to the x-axis, finding this area, and there's just an infinite amount of area. So what we say is the integral from 2 to infinity of 4 over x dx, we're going to say this diverges. It doesn't go to a number. So it goes to infinity, it blows up. We don't know how big it is. The area cannot be contained as a number, so it's going to diverge. So we have an integral, and it has an infinity in it. We have to rewrite it using limits. Six, 7, it says estimate the integral from 1 to infinity of 4 over x squared dx. So go ahead and pause the video and try this. Welcome. So we need to rewrite it. Notice the infinity, rewrite. So we have the limit as, oh, we can't use x. We're not using x's. I used t in the last problem. A lot of books use t. I'm going to use z here. Z goes to infinity. Oh, from 1 to z of 4 to the negative 2 dx. So I'm going to rewrite this 4x to the negative 2. And then I'm going to integrate this. So the limit as z goes to infinity. Remember, when we integrate, we add 1. So we get 4x to the negative 1 divided by negative 1. Made that parenthesis a little bit larger. Evaluated from 1 to z. Okay, I'm going to rewrite this one more time. And I get the limit as z goes to infinity, negative negative 4 over x from 1 to z. Okay, I'm going to plug in z. I'm going to plug in 1. I'm going to take its limit. All right, so we get the limit as z goes to infinity of negative 4 over z minus negative 4 over 1. All right, so taking this limit as z goes to infinity is negative 4 infinity. And plug this in so you guys can see it. 4. When I have a number divided by infinity, I am taking number and dividing it by something very, very, very large. We can do a quick key table. So if I have 4 divided by, I'm just going to do negative 4 divided by 100. And I get 0.84. And then divided by negative 4e to the point negative 0.7 is like 0.00000 negative 4. So that's, I'll write it, I'll type it out. So let's see my negative. Negative 0.1, 2, 3, 4, 5, 6. So notice as I'm dividing by larger and larger numbers, my whole number is shrinking. Or my entire number, it's not a whole. So I get really 0 plus 4. This tells me the area, here's the curve, here's the axis, probably to infinity, the area under the curve, so from 1 to the x-axis, is approaching 4. It's converging to 4. It's getting closer and closer and closer to 4. Diverge, it's diverging away from a number. It's getting away from a number. It's not getting close to anything. This converges to 4. It is approaching things converging. That's the area on the curve to the x-axis. Our curve is y equals 4 over x squared, going from 1 to infinity. Okay. So moving on to example 8, it says evaluate the integral from 0 to 6 for 4 over x dx, or explain why this cannot be done. Remember, I'm going to drop to the bottom and write this. The fundamental theorem of calculus states that f of x needs to be continuous over the domain in which you're integrating. Oh, yeah. We are integrating from 0 to 6. So from 0 to 6, we are integrating. Notice the curve here. So I'm trying to find the area under the curve from 0 to 6, but it's not continuous. At 0, it is not continuous. So we have to use limits. So to rewrite this, we're going to say the limit as t approaches 0, integral from 6 to 4 over x dx. I'm going to integrate this. So I get the limit as t approaches 0 to 4 ln of x from t to 6. I'm going to plug in 6. I'm going to plug in t. So I'm going to take the limit as t approaches 0 from 4 ln of 6 minus 4 ln of t. Just evaluate ln t. The graph before looks like this. So y is approaching infinity. So what we get is 4 ln of 6 minus negative infinity. All right. Those negatives cancel. And so I get 4 ln6 plus infinity. And so we get infinity. So the integral from 0 to 6, 4 over x dx is infinity, and it diverges. The area diverges. On the next page, there was room in case I ran out of room. We got it all in there. I didn't realize I had an extra page. All right, guys. If you have any questions at all, feel free to email me, and I will get back to you as soon as possible. And I hope you have a great day.